Good morning, folks. Thanks for joining us for this month's Database InMemory Office Hours. On the call today, you've got the InMemory guy, Andy Rivenes, and myself, Maria Colgan. We'll do our best to answer any of the questions you may have about database InMemory, and specifically in this session, we're hoping to explore join performance. Andy's going to start us off with giving us some background about how joins work in the Oracle database, as well as where they're getting benefits from using the data in the InMemory column store. And then you can feel free to ask any questions you may have during the course of the presentation and then in the open Q&A session via the chat on the Zoom. So you ask the question on the chat. I'll make sure that those questions are addressed by Andy during the course of the presentation. With that, I'm going to hand it over to Andy and let him get started.
Hello, everybody. Yes, so we have our focus on hash joins today, and so as part of database InMemory, and I did a lot of done a lot of touring in the last month or two with talking to different folks for both user groups and customer sessions. And hash joins are what database InMemory uses to speed up join performance. And I thought this would be a good topic both from our series in office hours and then just as a review and kind of a more deep dive explanation of how database InMemory leverages hash joins. So again, my name's Andy Rivenes. I'm a database InMemory product manager, and we have Maria Colgan, who's also a master product manager, but has database InMemory near and dear to her heart as well. She's graciously willing to help us out with the logistics. And with that, I think we'll go ahead and get started. I'm taking Stephen Feuerstein's advice, and we're just going to use my desktop in its entirety rather than trying to flip between different screens. So just bear with me for the presentation, but we'll leave it in just standard PowerPoint and without the view of the whole screen. That's our safe harbor statement. But let's dive right in. So join types in Oracle. So we have multiple join types: nested loop joins, hash joins, sort merge joins, and Cartesian joins. Database InMemory, though, leverages and focuses primarily on hash joins, and we have some special performance options we've added to the ability to use hash joins. The optimizer obviously chooses that based on cost, because typically we're joining larger data sets where, again, database InMemory is all about analytic style queries, and so that's what makes the most sense for most analytic type queries, especially when you consider star queries and data warehouse type joins, and when you're looking through lots of data. And so hash joins is primarily what we're going to focus on today, which of course is what database InMemory focuses on. So characteristics of a hash join. So sometimes folks kind of forget how hash joins work, so I was going to go through a very quick reminder of how a hash join does work, and then talk about how database InMemory leverages hash joins. And I've got some demos, so we'll do some live SQL, kind of how we've done the last previous two office hour sessions, so that you can see it in action as well, so you don't have to stare just at the PowerPoint screens. In addition to that, if you have questions, especially if they're particular to what we're talking about, that would be great. If you have more generic type questions, we will have time at the end to try to go through all of those questions as well. But I think the takeaway for hash joins is typically joining relatively large amounts of data, which is, again, why it makes sense to leverage with database InMemory. It has to be an equijoin. So I have my example here where our typical line order table and our date table where we have an equality predicate filter. We only join 2 row sources at a time, but keep that in mind because we're going to talk a little bit about something that database InMemory leverages with the Oracle and the optimizer. The optimizer is pretty sophisticated, so we're able to, what I like to call, cheat and actually leverage multiple sources. But in general, a join is made between 2 row sources, and with hash joins, there's a build table and a probe table. We'll kind of go through that, but I tried to put just kind of a join summary, my very quick join summary. Hopefully the optimizer lady won't have any issue with that, but we won't go into super detail because we don't have a huge amount of time. And to be honest, all of this is documented very well in the SQL tuning guide in the Oracle documentation. So if you have questions about hash joins in general, or hash joins with database and memory, we talk about it in our in-memory guide. So there's plenty of additional resources for you to go and explore the nuances of how all of this works if you're interested. Bottom line is, though, that we have a build table. It's typically the smaller of the two tables being joined. We create a hash table on the join key. I'll show you a couple slides and then obviously an example how that works. And then the second table, or the probe table, then is scanned and accesses the hash table to see if there's a match. And then matches are passed back to either the next step, or depending on if the query is just the two tables themselves, back to other processing within the query. So we have a nice slide that I've changed up a little that I think Maria originally probably did when we first introduced database and memory. And this is really just how a hash join works. And so as I mentioned, we have actually for the build table, we're joining two tables, the stores table and the sales table. I've made the stores table smaller to signify that it's the smaller of the two tables. And then we have our sales table. We're talking just row-based, a traditional hash join. We will get to database and memory in a minute. So that's why we have kind of a row depiction on the tables. The store table, we're going to scan. We're going to apply any filter predicates, and we're going to build a hash table in memory. And so that's the step one and then step two. That's my depiction of what the hash table will kind of look like in memory. I need to work on that a little bit. I'm trying to create a big presentation for all of this to make this a little easier to follow. But I think it's a pretty good depiction of what a hash table looks like. We have our hash, the actual hash, and then pointer to the actual columns that are associated with the rows that we've scanned in the stores table. We then proceed to scan the sales table, step 3. We apply any filter predicates. We hash the join key, and we then probe the hash table to see if we have a match. And for any matches, we can return those to either the upper layer of the execution plan, or perhaps we do a sort, or we just return that as part of our query if it's a very simple query. But the key points I think here are that we have a build table that we base our hash table on. There is, I won't go into the details, there is the possibility that the hash table won't fit in memory, so we may have to build a disk. But the bottom line is our goal is to be able to do that in memory and then probe that table based on the larger table, the sales table in this case, and see if we have matches. And that's basically, we're using a hashing algorithm, and that's in its simplistic view, a hash table, or a hash join, sorry. And then in an execution plan, and I'll show you this in our demo as well, we typically will read this as a hash join. The first table underneath the hash join will be the build table, and then the second table will be the probe table. And here we have our line order and date dim tables, typical of our SSB schema that we use for our database and memory demonstrations. And I just kind of wanted to show you what the execution plan itself looked like. So with database and memory, we're still doing a hash join, but now you notice that we have in-memory columnar representation of our stores and sales table. And so what we'll do is we'll scan the smaller table again, normal hash join. We will build a, well, I guess actually I'll go to the next slide and talk about that in a minute. But we have our join key, which is our store ID, and we have our filter predicate, which in the stores table is type equals outlet. And then we're going to join that to the sales table, but we're going to change things up a little with database and memory. We have some optimizations that make this up to 10 times faster than a traditional hash join. We get both benefits from scanning the data in memory in columnar format and all of the advantages that we talked about in the last two sessions with doing that. Plus, we're going to take advantage of something we call Bloom filters, Bloom filter technology. And so just as a precursor to that, I thought I'd have a little bit of a description of a Bloom filter. If you're not familiar with Bloom filters, they're actually named after a person who conceived these in 1970, Burton Howard Bloom. You can go do a Google search and get a lot of information on how Bloom filters work. But the gist of it for us is it's a very memory efficient way to test set membership. So we want to know, the hash join, we want to know, do we have matches between our two tables? And that's that's the bottom line with Bloom filters. You don't really need to know anything more than that. Bloom filters aren't new to Oracle database. We've been using them for various purposes since 10G. And the database and memory developers decided to leverage Bloom filters to essentially be able to turn the hash join that I had. Well, let's see, we'll go up this way. The hash join here essentially turns it into a scan and filter operation. We scan and filter the stores table, and then we can use a Bloom filter, which I'll show you in a second, to scan and filter on the sales table. And so this it avoids us having to go to the hash table and hash all of the join keys to see if we have matches. We can actually use a Bloom filter. And I'll skip right to that. So here's a depiction of how that works with database and memory. Notice that we're still going to create our hash table. We're going to scan the stores table. We're going to apply our matching filter predicates and return just the rows that we're interested in. But as part of creating the hash table, we're going to create a Bloom filter. And so with the Bloom filter, we're going to basically say, do we have matches for the rows? And then we're going to send that Bloom filter in step 4 as we scan the sales table. We're going to use the Bloom filter as another filter predicate. And so we can actually test our membership, our matches between the stores table and the sales table on our join key as we do the scan of the sales table. And that's really the power of the hash join with database and memory, being able to use that Bloom filter and do it during the scan. And I like to tell people that, one of our goals with database and memory is to try to do all of the work of the query, all of the work that we can for the query during the scan and filtering operations of the in-memory tables. And so this is another advantage that we have to be able to create or to run a hash join or a join between two tables very, very quickly within the scan and filter operations. Now, one of the properties of a Bloom filter, I think I put this here, is that it is possible that a Bloom filter can generate false positives. So that's one of the characteristics. It won't be, you definitely know that it's not part of the set, but it's possible that because we're hashing, that we might get a false positive. And so ultimately in our last step, we're going to go check our hash table to make sure that all of the rows we returned in step 5 actually match in the hash table. And so if they don't, then we'll cover that false positive ability of a Bloom filter. And that's kind of the steps of hash joins with Bloom filters with database and memory.
So Andy, we've got a couple of questions come in. So if now's a good time, let's try and hit some of those. First off, where are the payload columns or the other columns from the store table recorded while this is going on? Do I have to keep going back to the store table to pick those up? Where are they at?
No, actually, that was my. I don't know if you can see. I kind of highlighted that's my depiction here of all of the. So we have our actual hash table or hash array here, and then my picture, which is not very big, and I'll apologize for that ahead of time. We actually store it in the hash table, so we actually have all the payload columns right in the hash table, so that as we assemble the rows, we don't have to go revisit this stores table here. We have all of that information right here in the hash table. So it makes it very, very efficient then to just assemble or stitch the rows together to return them as the combined pieces to satisfy the query columns or the query itself. And I didn't say that very well, but that's
No. I think that's good. I think that it kind of addresses the question. The next one was, in order to get this Bloom filter, I need a filter predicate on which table?
So you need the filter predicate on the smaller or the build table. So that's where the filter predicate has to exist. If there's no filter predicate on the build table, then we won't be able to create a Bloom filter. We'll still be able to do the join, but we won't be able to take advantage of Bloom filter processing.
Okay. That sounds good. And then why are there these false positives again? That seemed to be a question, and I think it goes back to Dr. Bloom. We can blame on that.
Well, it's a characteristic of a Bloom filter because the Bloom filter is created by hashing the source or in our case that's our build table, and so a hash is possible to get collisions, and so collisions then could possibly generate a false positive because since we're not actually that's kind of an interesting in my depiction up at the top here. Collisions are why we would actually chain in a hash bucket multiples. You see there's two right here. Can you guys see my?
Yes.
There's actually two. So we may have to have a linked list of collisions. And so in the Bloom filter itself, we can't we don't have a linked list. So it's possible that it could be one or the other of these two that hash to the same value. And so we pick those up as a false positive, and hence why we check, whoops, I keep clicking on the wrong, hence why we have to go back and check the actual hash table to ensure that all of our matches are really matches.
I see. So there's no visibility into, we get the hash value, but we've no visibility into which entry on that linked list we're actually going to, whether we've got a match or not.
Correct.
What you're saying. Okay. Sounds good. Hopefully that addresses the questions, the person who asked the question. If you've got any more questions, please don't hesitate to use the chat function on the meeting. Send those questions to me and I'll make sure to ask them to Andy. So you want to keep going?
Yep. Great. And again, we're just taking you at maybe not the 30,000 foot level, maybe the 10,000 or 5,000 foot level, but there is plenty of information about how this works in the InMemory guide. We go into some detail about that, and obviously also the SQL tuning guide about how a hash join and how collisions occur, how the linked list, and we can actually traverse the linked list to find the different entries that might be part of the collision, or also if we have to build a disk with the hash table itself. So we're not going to try to cover all of this, but we do want to give you a good flavor for what we're doing and why hash joins are so much more performant within database and memory.
So before we move on, I guess we're going to get to it. That's the next question we just got. How do I know if I got a Bloom filter? So it looks like you're going to tell us anyway.
I am going to tell you. So yes, great question, because it shows up right in the execution plan. And that's one of the other takeaways with a lot of what we've done. Since database and memory is fully integrated in Oracle database, there's no guessing. I put that right there. You can actually see that a Bloom filter is used because you see in line ID 3 there, a join filter create, you'll see a :BF, and then you'll see a join filter use. So what we're doing here is we're actually creating the Bloom filter on the date dimension table, and then we're going to use that Bloom filter when we scan the line order table. So if you think about it, rather than having to actually do a traditional hash join, we're able to create the Bloom filter as we scan the build table or the date dimension table, and then we're applying that Bloom filter, or effectively conducting the join while we scan the line order table, and of course apply any other filter predicates. So this is why we say that we can actually turn a hash join into a scan and filter operation. And you see that right in the execution plan. And I actually have a demo where I wanted to actually show a little bit more information about that. So my tradition of not having to do any typing if at all possible. And this is basically the same demo we've used for the previous two sessions. So if you recall, in our first session, we showed how we populate everything into the column store. We have actually I could just do that. Oh, I don't have the, well, I was going to show you the population, but I don't have that in my script. So we've populated our SSB schema. It's fully populated in the column store. It's actually also fully cached in the buffer cache. Not that we're too worried about that performance comparison at this point. And we've shown you how we do scans. So we've kind of gone through the basics of database and memory. And so now let's take a look at a traditional hash join. So I've got the no in-memory hint, because with the tables I am going to query are part of the column store. So we want to avoid that to show just a traditional hash join and what it might look like. It takes a few seconds since we're not doing in-memory on actually 16 on our demo. But notice now we have the same basic query that we had in the example. And we see our hash join here. The first table will be our build table, date dimension table, and it's smaller than the line order table, which is our fact table. And we do our hash join. In this case, we'll do a sort and return those rows back to the query, which were right there. We were looking for revenue. So now let's take the same.
Andy, before you move on, I noticed you used the no in-memory hint, but is there anything else in the execution plan that indicates the in-memory column store was not considered or used for this query?
Yeah, good point. Well, it was not considered. Yes, it was not considered in the sense that we have our table access full, so we don't see table access full in memory or table access in memory full. So we know that we didn't actually access the column store as well. Good point. Yeah, that was lesson or office hours 2, but that's always good to review. Thank you.
Well, I missed office hours 2, so you have to forgive.
No, that's fine.
You have to forgive me on that one.
No, because folks, well, that's a good point, because folks that come in maybe haven't looked at some of the other sessions, and is a good review to show that, yeah, this didn't use database and memory. And the main reason we did that, or I did that, was so that we wouldn't, I'll actually show you why, because when we actually don't put our in-memory hint in, not only does it run screaming fast, but what we now see is not only our table access in-memory full, but because we did take advantage of database and memory, then we see the join filter create with our Bloom filter and our join filter use with our Bloom filter. Now, the reason I wanted to run the demo in this particular case is I also wanted to show you that in the predicate information, you notice that we have our in-memory, and we kind of reviewed this prior, but what we'll see now is we'll see both the traditional filter predicates that we would see with without database and memory, but it will tell us what we leverage for filter predicates in memory. And that's very key, because notice that we have the sysop Bloom filter function here, which tells us that we actually used our Bloom filter we created in step 3, and then used it in step 5, but applied it in step 6 to the actual scan of the line order table. So this is how we know that we actually use that Bloom filter as part of the scan. And notice, in addition to that, our other filter predicates that we have. So when it's not an all or nothing kind of thing, we can actually use other filter predicates all combined together to scan the line order table, and hopefully do as much, if not all, of the work that we need to do for the query during the scan and filter operation.
And if we go back up to your query, are you saying then that that LO order date is the join column? That's why we're creating the Bloom filter on that? Was that your join column between the two tables?
Yeah, so we have LO order, line order, and date dim.
Yeah.
And then we have, this is our equality predicate.
Okay.
Right? And then we have actually on our date dimension table, we have filter predicate here, so we can create our Bloom filter. And then we have our other filter predicates that were included on the scan.
Perfect. So that's why it's LO order date in your Bloom filter, because that's the join column. Makes sense.
Okay, so that's that part of the demo. So let's go back and talk about multiple Bloom filters. So it's not just a single Bloom filter, but especially for more sophisticated queries like star queries or multiple table queries, we can actually create multiple Bloom filters. And so that allows us then to do essentially the work of multiple hash joins in a single scan and filter operation. So we still can maintain essentially our goal of doing the hash joins, whether they're one or multiple hash joins, as literally a scan and filter operation all the way through the query operation or the execution plan. However, you might ask, well, so how can we do that? Traditionally, a hash join or a join, I remember at the beginning I said that a hash join typically joins two row sources. So in this case, in a normal execution plan, we would join two tables, and then take the results of that and join our third table and our fourth table and traverse up through our execution plan. And that's typically how folks read an execution plan and how Oracle will process that. This is where I said we actually get to cheat in our execution plans, though. There is the ability in Oracle, since the optimizer is very sophisticated, and the PowerPoint presentation steps through this, so bear with me because I'll just do this on the fly. But this is where now we can actually do something we call swap join inputs and create a right deep tree. So this view was a traditional left deep tree, which is what most Oracle execution plans will have, is a left deep tree type query. So we'll join two row sources at a time and traverse through the execution plan until we've joined all of our row sources and return the result. With database and memory, and there are some other execution plans that will take advantage of this, the optimizer can swap the join inputs and create a right deep tree. Now, I'm not going to attempt to explain in great detail how left deep trees and right deep trees work. We do explain this in the SQL, you chuckle, but we do explain this in the SQL tuning guide. And of course, you can go through Google and get to the academia. There's lots of
white paper.
Academic white papers and all sorts of, there's lots of information. This is not an Oracle unique process. This is a relational management system RDBMS and relational theory. And so this is just a way for us, though, to what I like to say, we get to cheat. And so what I mean by that is that with a right deep tree, the characteristics is we're able to actually scan each of our dimension tables, in this case, the smaller tables that would normally be joined in a left deep tree one at a time to our largest row source. And we're able to create our hash joins, or a build table, we're able to create our hash table in memory, and at the same time create our Bloom filters. So this is the Bloom filter here. So what we can actually do is well, and this is the part what I call we kind of get to be able to cheat, because we can do our scan and filter operation on each of our build tables. We can actually create the Bloom filter, because we looked at our traditional or our two table in memory join, and we know as we build the hash table, we can create the Bloom filter at the same time. We can do that as we traverse down the execution plan, and we can end up with 3 Bloom filters, and then as we scan our line order table, applying our filter predicates, we can also apply the Bloom filters. And so we can do this because we've swapped the join inputs and we changed this into a right deep tree. And so what this does imply is we're going to carry all of these hash tables in memory. So it is more memory intensive, but the advantage here is that we can then apply all of those Bloom filters during the scan of the line order table, and we can actually reduce the amount of rows that we have to carry through the hash join, which is what we have to do in this picture. We have to carry a lot more data up through the execution plan. And of course, it allows us with database and memory to leverage the Bloom filter so that we only have to scan the line order table or the data that's in the line order table once. And then of course we have on the right side here, our 1, 2, and 3, and that's where we're going to go verify that we don't have any false positives in our hash table as we traverse back up the join path to return the row set that we had for this join. So that's how we can have an execution plan that looks like this. And if you look at it, it kind of looks like it goes off to the right. It's not a definitive way to look at it, but conceptually, what it allows us to do is we've traversed the execution plan, and we've looked at the supplier table, created a Bloom filter in our hash table. We've looked at the date dimension table, We've looked at the part table, and then we're going to take our 3 Bloom filters that we created and scan the line order table. So a little complicated, but very sophisticated, and the bottom line is it leverages Bloom filters with database in memory so we can have multiple Bloom filters and not have to do multiple amounts of work.
Before you jump into your demo, Andy, we got another question, and it might be worth going back to slide 9, I think, probably where we want to go. And the question is, can you give us a little bit more detail about the bit vector creation based on the join values? And it came in while you were talking about the multi-table Bloom filter, or the ability to have multiple Bloom filters in a single table. And I don't know about you, but I always think of these bit vectors just like a bitmap index. And Oracle's able to apply multiple in a similar way that we're able to apply multiple bitmap indexes. But I don't know whether it's probably too much detail to get into exactly how they're built. But effectively, you can think of them, at least I do always, as like a bitmap index, where we've got a hash or a representation of a positive value represented as a 1, and no entry is represented as a 0. But sorry, I'm answering the question, but
that's perfectly fine. That's kind of why we have both of us here. That's great. Yeah, and I think the only other takeaway is that there will be one of these bit vectors for each of the Bloom filters. So it isn't like we're trying to combine this array in multiple, like a multi-dimensional array of any kind. It's not that sophisticated. It's literally just the Bloom filter in a bit vector or Bloom filter for each of the Bloom filters, each of the tables. And yeah, like I said, we don't have enough time to get into the gory details, but again, there's lots of information out on the internet how Bloom filters are constructed, what this actually looks like, how it's hashed, and it's hashed multiple times. There's a lot of details, and it's much easier, I think, if you just go read literally the white paper that describes in detail how that works. But that's the gist of it. You're right, is that the bit vector, and it just tests set membership. That's really the simplest way to think of it.
It's the goal of it, yeah. And as I said, in my mind, it's easier to kind of think of them like a bitmap index. If you're familiar with that concept of the entries, and an easy way to kind of find a positive yes or no set membership test, as you said. So hopefully that helps address the question.
So here what we see is the same basic execution plan that I showed you earlier in the demo, or in the actual slides. We have our supplier table, we have our date dimension table, and our part table. And noticed we've created Bloom filters for each. And then we apply all 3 of those Bloom filters to our scan of the line order table. Now, one of the advantages, there are multiple options in DBMSX Plan, which is what I'm using to display the execution plan here. Normally, we would use SQL Monitor reports, but SQL Monitor doesn't give us the ability to look at some of this other information. And what I wanted to show in the outline data, if I can get my mouse to let me go back down to where we were, you can actually see the swap join inputs.
Yeah, you can.
So you can actually see what the optimizer is doing, and it's considering all these different access predicates, or that's not the right word. All of these different, what's the right word, Maria, for what we're seeing in this section?
What you're looking at there is the outline, which is basically the set of the exact set of operations or hints, so to speak, that would get you, that would reproduce this plan. So
I didn't want to say hint, but that's kind of what it's doing.
It's pretty much what it is, yeah. The outline is the complete set of hints required to reproduce that plan.
Right, and the query blocks identify where in the execution plan we are, but you'll notice that we got our join filter for the Bloom filter creation, or swap join input. So you can actually see, given the right options, options to DBMSX Plan, you can actually see all of what's going on within the execution plan. Of course, you could obviously do an optimizer trace as well. But if you're interested in diving into the nuts and bolts, we don't really hide a lot of this from you. We actually, it's available for you to go investigate if you're interested. But I did want to show that is actually occurring, that we are actually having to do a swap join input in order to get our plan to look like this so that we can actually, pre-scan, if you will, or scan ahead of time the dimension tables so that we can get those bloom filters to be able to use them to scan the line order tables. So again, it goes back to, we're trying to make one pass over the data, and we're trying to do all of the work we can as we scan that data. And what it gives us is phenomenal performance. I think I left the timing on. It took 1 minute or 1 second and 3/10, basically 1 second to run this query, and it takes much longer. It actually takes 11 seconds in this system. That was in, if you want to go verify that, you can look at the second office sessions we did, but it takes considerably longer. It's basically a 10x performance improvement over the traditional hash join without database in memory. And then there's just more information here about what the query is doing. And again, we have our information about our predicate information as well. So with that, I will flip over because I don't want to take all of the time on this, but I think this is valuable to show people how this actually works.
No, it is very valuable. And I know you have to bear with some of us who didn't see the second office hours in this series where you covered this scanning part. But can you very quickly just give us some of the advantages of why you're trying to move everything to that scan operation? Why is it so much more efficient to scan data in the in-memory column store?
Oh, sure. Yeah. So table access in memory full. So not only are we scanning the data columnar format, so we only have to access the columns that are part of the query. We don't have to access all of the columns in the row or all of the row. In a traditional, the row format, we have to traverse each of the rows in order to get to the columns we're interested in. With our columnar formatted data, we can access just the columns that are part of the query. In addition to that, those columns are compressed, and since they're in columnar format, we get a very good compression ratio, usually anywhere from 2x to 20x compression. We have in-memory storage indexes, so if the values that are in each of what we call IMCUs, or the extents that we populate the object into the column store in, we can actually skip over data if it doesn't match, if we're not going to find the data.
So a bit like partitioning.
Yeah, it's a bit like partitioning,
pruning, yeah.
and pruning and partition pruning. Exactly, that's a very good analogy. And then SIMD vector processing. Since the data is columnar formatted, it's basically in a vector-friendly format, and then allows us to use SIMD vector processing, what I like to call array processing, to do our comparisons or look at the column values in chunks rather than one at a time. And so we go from scanning millions of rows per second per core to billions of rows per second per core. So that's the kind of the technology end of database and memory of the scan itself. And then what we're talking about is one of the optimizer enhancements. The optimizer allows, based on cost, or will choose to do a hash join, create bloom filters, and leverage the execution plan to take advantage of the technical part of database and memory.
And all that goodness you talked about, the compression, the storage index, the vector processing, I'm getting all that for free once I put the data in the in-memory column store, right? I don't need to do anything else to get all of that goodness?
Yeah, exactly. So in-memory underscore size is greater than 0, and when you've created the column store, basically that enables database and memory, and that's a trigger for the optimizer that says, oh, I can now take advantage of some additional access methods to the data that I couldn't without in the in-memory column store enabled. Because even if some of the tables, for instance, like say the supplier table wasn't populated in the column store, we could still take advantage of a bloom filter and the scanning of that and still access the line order table in memory with a bloom filter. It wouldn't be as fast because we obviously would have to look at access the row store to get the data from the supplier table, but we would still create the bloom filter when we created the hash table because database and memory was enabled.
So as long as the line order table was in memory, we'd still get some benefit. That's
yes, typically, because I mean, yeah, if nothing's in memory, then even if you used bloom filters, you're still scanning through the row data in the buffer cache, so it's not going to be, you're not going to get much of any advantage of that. And actually, the optimizer probably won't choose that access path anyways. But yeah, it doesn't mean that you have to have all or nothing, which is an advantage for some folks because, you know, not everybody has all of their schema populated in the column store.
No, it's a really good point.
Unfortunate, but
you gave us another little hint in something you said there, Andy, that I just want to make sure folks heard it. You mentioned the fact that the optimizer is in memory aware. Can you share with us just a little bit what you meant by that, that it knew that the line order was in memory?
Sure. So once we know we have a column store allocated, and you've done an alter table line order in memory, then that flag, then we'll in the background, either on first access or based on a priority, we'll populate the line order in the column store. And then at parse time, the optimizer will take a look at any of the objects involved in the query that are populated in the column store and take a look at how much of that data is populated, how many of these extents or IMCUs are available, and use that in its cost mechanism. So it will cost out, does it make sense to access that data in the column store? Should I use Bloom filters? Should I, basically we only have one access plan, table access in memory full, but does it make sense to do that? Or maybe based on cost, it makes sense still to access that data through an index in the row store, because maybe it's an OLTP query and an analytic queries in a mixed workload environment. So not all queries have to go to the column store, that some could still access an index because maybe you're only looking at one or two rows.
So it's fair to say we get some extra statistics from the in-memory column store to help the optimizer to make those decisions and to be able to do these kind of optimizations that you're sharing with us, the Bloom filter and the multiple Bloom filters. So that's pretty neat.
Yeah, and actually in 12.2 in the all tab columns, I think it's all tab columns, we added a couple, and we talk about this in one of our blog posts, we added a couple of, or we persisted what the optimizer sees at the hard parse into a view, so you can actually go look and see what the optimizer saw. And so you can also do that through an optimizer trace, but optimizer trace is kind of and it's a pain to create, and you can actually just go see it in a dictionary view. So our user tab columns, I don't remember off the top of my head, I don't remember the exact.
User tab call statistics or user tab columns stats?
Yeah, it's one of those.
User tab call statistics, I think, is the.
Actually, I'll have to go back and look. That's actually would be a good blog post to add, because I'm pretty sure we talked about it in one of our blog posts. I do talk about it some of my presentations, and maybe based on that, since I can't remember the exact, it's hard to remember all of the different views, we'll just do a short little blog post for that. That's actually, because that was a 12.2 enhancement.
Right.
It's
the persisting of those.
Yeah, so we're doing in 12.2 and now 18C, we're adding enhancements and additions to make database and memory easier to manage, and we're trying to squeeze as much CPU performance as possible, which is kind of the segue into the next topic. So we'll tackle that, and then hopefully, well, we're going to run a little short on time. I don't know how many questions we'll have, but as the segue, so what happens if you don't have a filter for a hash join? We're not going to use Bloom filters. Or we're trying to squeeze a little extra performance out of joins we know we're consistently doing. Think of maybe in a data warehouse or maybe a BI system where you're consistently joining certain tables together on certain columns. And we're not, even if you do use a Bloom filter, you get some benefit, but it's really meant to handle the cases where there aren't Bloom filters being created based on filter predicates. We have a feature we added called join groups in 12.2. The ability here is you can create or tell the database commonly joined columns and create join group. This is the syntax. I'll show that to you in a minute. And what we do is we then coordinate the dictionary values between the two or multiple tables, depending on how many you tell us there are in the join group. And it gives us the ability to avoid having to decompress and evaluate each of those dictionary values, because we're now coordinating them between multiple tables. Part of this goes back to the ability for we want each of the objects we populate in the column store to be able to stand on their own. And so we didn't initially create join groups because we don't necessarily know what columns are commonly being joined. We didn't want to create huge common dictionaries because that would take up a lot of space and might not ever be used. So what we did is we allowed you to tell us which commonly joined columns are on tables are being used, and you can tell us to create a join group, and we can coordinate that. And what we're really after here is to save CPU cycles, because with database and memory, really all we're doing is accessing, or we're using CPU to access memory. And so the way to speed that up then is to use less CPU.
Great.
So it allows us to save on decompression and hashing. And so I have an example. I didn't want to go into a huge amount of detail because I was afraid we would run out of time. But there is a create in-memory join group syntax. And the depiction here is if we have commonly accessed columns between multiple tables. In this case, we have our vehicles table and our sales table. When we do our population, and we do the compression on each of those columns, we will coordinate the dictionary values, because we use dictionary level encoding as one of our primary space savings for compression. And we'll coordinate those on the columns you tell us that are commonly joined. And then we don't have to decompress or evaluate those dictionary values independently. We know that they're common to each other, and so we can actually do the join directly on those columns. So that's kind of oh yeah, you have
I have a question, sorry. I know you're a compression aficionado, right? But for those of us who are still doing kind of Sesame Street approach to compression, is it true, based on the slide that you're showing me there, that for this common encoding that you've mentioned, for each value that I have in the vehicle name column, I'll represent that value, in this case, as a number, as some kind of symbol, and then each time that name appears in the table, I replace it with the symbol? Am I right in thinking that's how it works?
Yes, exactly. So the dictionary level encoding, basically it allows us to think, if you think of Cadillac or Porsche, which are long, much longer than VW, but you could save quite a bit of space if Cadillac shows up all over the different for the row representation in the column format for that column. If we can just replace that with a bit mask, or a number of bits, a number, whatever you want, conceptually inside, it's just really a bit string. We can save a considerable amount of space. And we use a somewhat similar algorithm in advanced row compression as well. Obviously, it's different because we have on disk savings, we're trying to compress on disk, versus in memory, we're trying to compress in memory. So we want to make it vector friendly, so we can use our SIMD vector processing.
Okay.
But we do save a considerable amount of space with things like dictionary encoding. So we create a dictionary for the vehicles table, and we'll create a dictionary for the sales table for the commonly used dictionary values, and we'll just replace in the actual column stream the symbols rather than the actual data itself. And then in addition to that, in our example, if we have a common join column, if we create our join group, we'll coordinate that between the two. And so that's where we can not only save space, but then save on having to spend CPU evaluating what those values are in the dictionary, because they're common. So we can literally just join on those dictionary values. And we know we can have set membership that way. So all we're looking for is, do they exist, right? We don't actually care what the column is, as opposed to just knowing that it's the same value in both.
Right. So in your example here, like for Cadillac, as long as it's a 2 in the vehicles table, then if I find a 2 in the sales table, I have a match.
Right. We don't really care that it's Cadillac until we actually return to the upper part of the query. So just for the join part of it, all we need to know is that it's the same value.
Okay, so we'll do the join on the symbols or on these values that we're using in the compression dictionary, and it's only after the joiner that we'll actually do the decompression and turn them back into Porsche and Cadillac and Tesla and so on.
Yeah, exactly. And you think about it, it's decompression, people will usually think of like I have to unzip or I have to do, and
Right.
really we're only talking about is just retrieving the actual value out of the dictionary. So decompression is what it is, but if you think about it, it's really just a lookup. So it's even less overhead to do a lookup. We don't actually have to change the value into something different. We don't have to unzip it, if you will, like if you had gzip or winzip or something.
Okay.
So it's actually very efficient even to access that data. So that's where we say we're able to access directly on compressed data. And people sometimes will kind of look at us, but if you think about it, it actually makes a lot of sense.
Cool. Thanks, Andy.
So my last demo, I wanted to show an example of using a join group. So I wanted to show you what join groups look like or how you could query them. And I've already pre-created these. And so the first part of this is the actual query. There's a view called user join groups. And I see that on my line order table, I've created join groups for order date, part key, and supplier key. And actually, what I did here is I created a comment so you could actually see how I created those. What I did is I actually ran that syntax, and then I repopulated my tables into the column store so that we could take advantage of the encoding. We have to repopulate because we have to be able to sync up the values together. Sorry, it's hard to do this on the camera.
No, it makes perfect sense. Now that we've seen the picture, I think that in order for them to share that common dictionary, once you give me the join group, we can establish the common dictionary, but then we've got to repopulate the tables to make sure they use that common dictionary. Makes sense.
Exactly. And then if you, we'll go ahead and run a query using join groups. And that was our query before. And I don't show you an execution plan because it isn't any different. You can't tell from the execution plan, well, we'll qualify that, but from a normal like DBMSX plan, you can't tell that we use the join group. What all of this here is from one of my the labs that I do. We create a SQL monitor report. So that is a way to tell whether to use the join group. So all that gobbledygook there is would be saved into an HTML file, and I access this. And so what it does is it creates this file here. And this is a SQL monitor, what we call a SQL monitor active report. It's the easiest way to visualize this. Actually, SQL developer, the guys, Jeff Smith and company, are working to actually make this available so you don't have to run necessarily this Flash version of it. You'll be able to do this directly in SQL developer, because if we look at our binoculars here, let's see if I need to go down to, we'll pick, for the hash join, if we look at these binoculars, you can click on that, and it'll give you some of the other information that is associated with the join or the operation itself. And notice we have columnar encodings leverage. It's not highlighting on the screen, sorry. But the very last one says columnar encodings leveraged 1. And that means we used a join group as part of the query, and that's how you can tell. There's actually a columnar encodings observed and then the leveraged, because we actually have some other optimizations, and I talked about this, and we have actually 2 blog posts that cover join groups. So if you're interested in some of this information, you can go take a look at those blog posts. The bottom line is that's how you can tell whether you used or leveraged the join group. We're working to try to make that a little simpler to see, but for now, because it actually occurs at the execution level, not at the scan level. I mean, it occurs at the scan level, but it gets reported in the multiple layers of Oracle. We actually don't get this information reported to us until we're into the execution phase, after we've already left database in memory, if you will. So that's why it shows up.
I'll also see it in the elapsed time, though. Hopefully it'll be a little faster.
It'll be a little faster. It's not like orders of magnitude. It's not like the hash join Bloom filter 10x performance improvement. But in most cases, you'll see a performance improvement. It'll typically be in the tens of % improvement rather than the
hundreds
X, your orders of magnitude. But it's still, remember, we're trying to save as much CPU time as we can, and across, again, we're doing this for commonly joined queries. And so across a large workload, this can add up to a significant CPU savings. And again, CPUs are relatively expensive, CPU cycles. And so the more you can save, the more queries you can run, and maybe the less you have to buy. So again, leveraging that, and especially in a mixed workload environment, to be able to run real-time analytics, be able to run analytic queries right on source data in essentially your OLTP system or your mixed workload system.
Is it also true that I might be able to save a bit of memory and perhaps prevent a big, a join between two big tables spilling to disk if I leverage this, given the fact that the values I'm working on are those symbols rather than the actual values?
Sure, yeah, we should save memory in the PGA because we don't have to access all of that information translated, basically, right? So we don't have to compare the full value of the full value. We can actually just work on the dictionary symbol. Yeah, so we should see less PGA usage in addition to that. Although I don't have any concrete examples of how that would work. That's pretty data usage dependent. But,
of course, yeah. But ideally, it would help a little in that way. And as you said, then you put it in a mixed workload environment where the system's already very busy in terms of CPU and memory, and you might just be able to get some more extra mileage out of those CPUs, let's say.
Like where additional information is available. Obviously, I've mentioned our blog, and the URL is right there, blogs.oracle.com. My email address, if you have questions. I strongly recommend, if you want to dive into this even deeper, that the documentation is very good. The in-memory guide and the SQL tuning guide, which I'm sure you have a vested interest in, or at least you used to. And so there is additional information. And I don't know if we have we have a few minutes. Are there any other questions?
So the first question is, will this recording be made available? And
that's all the Ask Tom recordings, this one included, will be available. Usually it takes us a couple of days, and we'll have it out. And but it will be available.
So you also got some nice compliments in the chat. Great presentation, but I think my head's about to explode.
Oh, good. I like that.
Friday, it was a lot of technical detail, but
it was.
Say, right, there is a lot of white papers, a lot of information in the documentation too, that if you heard something and you're trying to figure it all out, there is lots of places, right, where people can go to get more detailed information.
Right. I mean, that's kind of the conundrum with a lot of Oracle technology. We really do try to make it simple to use. I mean, all you really have to do is allocate the column store and alter the table in memory. And in almost all cases, the optimizer takes care of everything. But sometimes it's nice both to know what's going on under the covers, and if there are times where the query isn't running correctly, you can scan it at the execution plan and kind of say, oh yeah, there's something about bloom filters, and then you can go look it up, and I heard something. At least you'll know that it exists. So It is kind of a two-edged sword. It is simple, but there are a lot of details under the covers, and so hopefully your head didn't really explode, but I guess it's Lloyd, but still, that's a kind of, it's nice to know that, that you guys are looking at this, and that we're at least trying to provide some of this information for you.
Right. And at the very least now, you're going to be smarter than your colleagues. When you see an execution plan with that BF mentioned, you'll be able to say, oh, I know what that is. Andy told me that's a bloom filter. It's going to help improve the performance of our join, hopefully, so it's all good. So if nothing else.
Bragging rights, yeah.
Exactly.